All right, well, welcome to Notes 1.4, Even and Odd Functions. So we're going to explore even and odd functions from the graphical perspective and then from the equations from the analytical perspective. All right, so first of all, what's an even function? Well, we know there's lots of kinds of functions out there, but specifically an even function would be a function, a graph, that has symmetry with respect to the y-axis. Okay, so we're going to look at a few examples. All right, so we have three coordinate planes ready to look at three examples of what an even function would be. So pardon the sloppiness of the coordinate planes just because it's just kind of difficult to write with this pen. All right, if we have symmetry with respect to the y-axis, okay, well, I think the most obvious even function would be the parabola y equals x squared. So you know what I'm trying to draw. We'll hope for the best here. If I were to fold along the y-axis and fold here, okay, both these branches of the parabola would lay on top of each other, coincide. So we have symmetry with respect to the y-axis there. All right, well, what if I took another parabola and I opened it down, but its vertex still fell on the y-axis? Okay, well, if I were to fold along the y-axis, okay, the graph would lay on top of itself, so that is an even function. So we can pretty much say that parabolas whose vertex fall on the y-axis, okay, have the even property. All right, well, don't forget about the absolute value as well. So all three of these are examples of even functions. And with all three of these, if you think about it for just a second, if you were to shift them vertically, up or down, not left or right, but if you were to maintain the shape of the graph and just shift them up and down, there would be symmetry with the y-axis. So all three of these are examples of even functions. Okay, I want to look at some specific points that are on each of these graphs to make a relationship with the ordered pairs. So graphically we know what an even function is, but what does it mean about each and every individual ordered pair that belongs to these even functions? So for example, I'm just going to pick on this point right here. I don't know what the x coordinate is, so I'll just call it x. I don't know what the height is, so I'll just call it y. So if I look at its reflected point that belongs right here, what would be the coordinates of that ordered pair? Well, it should be the opposite x, but with the same height y. Same thing here. If I were to choose this point right here, it has some x coordinate, okay, and it also has some negative y. So what would be the ordered pair over here? Well, it's going to be negative x, but still a negative y. So the y's stay the same. They're not going to change in sign if it's symmetry with regard to the y-axis. All right, and likewise here, this would be x positive y, and this would be negative x positive y. So what we want to take away from the ordered pairs is this. We want to make some kind of general assumption about each ordered pair of every point on an even function. Well, let's just start with example 1 and 3. If I had an ordered pair xy, okay, it just means that if it's an even function, the x's would be opposites, but the y's would stay the same. So if the point started out as negative y here, then it would stay negative y here, and the only thing that we're seeing that changes would be the x's are opposites. All right, now we're going to look at an odd function. All right, so an odd function, you might be thinking, well, that might be symmetric with respect to the x-axis, but actually it's not. An odd function has symmetry with respect to the origin. Well, exactly what does that mean? Well, that means that if there's symmetry with respect to the origin, there's two symmetries that have to take place. Okay. The graph has to be symmetric. You have to be able to reflect over the x-axis and the y-axis. And it doesn't matter if you reflect first over the x and then the y, or if you take the original graph and you reflect it over the y and then the x. It doesn't matter. But it just needs to have two reflections in order to be said to be symmetric with respect to the origin. Okay? So an odd function has symmetry with respect to the origin. Now notice that I left a little bit of space here when I put the word examples here, because we're going to go back in and do what we did just like up here with an even function. Look at the relationship of the ordered pairs after we look at some examples. Okay? we're going to look at 2 examples and 2 non-examples. Sometimes it's good to look at non-examples as well. All right. Okay, so a graph that has symmetry with respect to the origin, or an odd function, okay, would have the characteristics of something like this. Think of your cube graph, y equals x cubed. If you just study it for a minute, if you were to take in just this part of the graph that's in quadrant 1, and if you were to reflect it over the y-axis, I'm going to do the y-axis first, and then reflect it over the x-axis, what's going to happen is it's going to lay on top of itself. What if I did the reverse order? What if I took and reflected this graph that's just in the first quadrant over the x-axis? It would look something like down here. But then I wanted to reflect it over the y-axis. Second, it would lay on top of itself. So this is symmetry with respect to the origin. Let's look at another cube graph. I'll do the best I can here. Okay, so let's take a look at this one. Okay, if I were to take maybe this part of the graph that falls in quadrant 2 and reflect it over the y-axis, it would look something like this down here. But if I did a second reflection through the x-axis, the horizontal, it would lay on top of itself up here. If I were to take this part of the graph in quadrant 1 and reflect it across the, I guess we could go the x-axis, it would come down here. But then if I were to reflect it across the y, it would match it on top of itself right here. So graphically, this is what an odd function looks like. So let's look at 2 non-examples. I think sometimes that's good just so we have a deeper understanding. Oh, not bad there. Ooh, not so good there. All right, I'm going to look at 2 more cube graphs just to see that they don't line up. Okay, what if I took a graph like this and asked if it was even? Well, of course, it's visually, we can see it's not even, because if you reflect across the entire y-axis, okay, the graph's not going to lay on top of itself. Okay, but is it odd? Well, let's just think about it for a second. If you were to take this part of the graph that's in quadrant 1 and reflect it across the y, it would be over here somewhere. But then if you were to reflect it across the x-axis, it would have to start here and go down. And that's not going to lay on top of itself. Okay, let's look at another example. So it's almost like I'm hoping that you see that, I don't think that's the way it was supposed to turn out, but that's okay. Okay, that neither one of these graphs pass through the origin. So when it says it has to have symmetry with respect to the origin, at least part of the graph has to pass through the origin. Okay, so let's go back up here and look at some specific points. Okay, and the relationship that they have on odd functions. All right, so I'm going to choose this point right here. Maybe. There we go. And I'm going to label it XY, because that point's in quadrant 1. If I were to reflect here and then reflect again, 2 reflections, that reflected point, that odd point, are going to have the coordinates -x, -y. So I want you to just think for just a second. Okay, if there's 2 reflections, I'm going to have to change both ordered pairs. If they're both positive, they both become negative. Okay, well, let's come over here. Well, let's choose this point right here. Okay, well, the coordinates of this point would be +x, -y. Okay, what is its odd point? Well, if I were to reflect through the y and then the x, it appears that its point may be right here. And what is the ordered pair for that? Well, it's going to be -x, but +y. So for graphs that are odd, okay, we would have to change the signs of both the coordinates of the points of the ordered pairs. Change both the signs of both the coordinates. Woo! Got through that one. Okay, so let's look up here and look at all our different options. If we had xy and it's an odd function, then we change to -x and -y. If x is positive and y is negative, that means something like this, then its odd point would be -x, +y. Well, that's only 2 quadrants. Let's look at the other 2. What if I had a point up here in quadrant 2? Well, it'd have coordinates -x, +y. Change this sign and this sign, So its odd point should be x negative y, and that corresponds here. Okay, well, what if I started out by looking at a point that fell in quadrant 3? Those coordinates would be negative x, negative y, and when I reflected it twice, I would end up with positive x, positive y. So what I'm trying to get across here is that if you have an odd function, both the signs of both the coordinates would change. If you have an even function, only the x-coordinates would change. Okay, now we're at a checkpoint. Okay, part of your homework assignment doesn't give you graphs to look at, but they give you equations, and they ask you, are these functions even, odd, or neither? A lot of functions are neither because they're not even or odd. Okay, so what would we do in this case if we have a problem like that on our homework, if it asked us to determine if these equations were even, these graphs were even or odd? Well, I mean, type it into your calculator and look at the visual. I mean, I think we can see that this one right here without typing it into the calculator because we have background. Okay, that's a parabola that opens up, and it has a vertex down here at the point 0, negative 4. Okay, well, what is that function? Well, from what I see, the visual, it's even. All right, well, let's think about this. Well, from our background in math, we know this, again, is a parabola. Okay, and it's been shifted right 1 off its vertex, off the parent function. So if I shifted it right 1, had it open upward, visually, is this even, odd, or neither? Well, it's not even. There's no symmetry with respect to the y-axis. And it's not odd, okay, because remember what the ordered pairs have to do. Okay, so one of the points here, positive x, positive y, to be odd would have to be negative x, negative y. Well, I don't have any part of the graph down here in quadrant 3 where the coordinates are negative x, negative y. So we would say that this graph is neither. Simple enough. Type it into your calculator, look at the visual after you set a good window and view all characteristics of the graph, and then determine if the graph is even, odd, or neither. So in the next video, what we're going to do is we're going to determine if a function is even, odd, or neither, but we're not going to have a graph. Okay, and we're not going to have a graph and calculator. We're just going to have an equation. So what do we do in that, in that sense? Okay, how do we determine if a function is even, odd, or neither if we don't have a graph or a graph and calculator to graph and visualize it? Okay, and so we'll look at that in the next video.